So today, the good news is there won't be any homework tonight. So one of the things that we often will, we already did this, right?
Correct.
So
That's
we want to talk about the derivative of inverse trig functions. Okay. Now, here's more good news. You are not going to have to memorize these like you had to memorize the other ones, but I will not give them to you. So what will happen is I will let you have some sort of a note card for this. But you write it down in your note card wrong, and because you're in a hurry and forgot to do it, you're going to be kind of out of luck, right? So next class, we're actually going to kind of add to this. Mr. Westerbeck, with his classes, decided that there's kind of a secondary thing that he thinks you should add. I guess to me, it's more, what's the word? It's kind of spelling out how to use the chain rule inside of these. And so I don't know if it's necessary, but I'll play the game with him a little bit. So, gentlemen, for those of you who have had me, some of the things we've done this year, I've been a little uncomfortable in that I kind of given you the rule, but I haven't really taught you the why. And I guess to me, it seems like you got to know the why. So we are going to prove why this one is true. And the rest of them, you can imagine, are similar kinds of arguments. But I just want you to understand that these aren't just magical that someone created. There's a reason why we're studying them now when we're talking about what kind of derivatives? Spit your gum, please. Spit out whatever's in your mouth. What are we talking about? Why am I implicit?
What kind of
implicit differentiation? Okay, so we're talking about implicit differentiation. So I'd like to just prove this first one with you. Okay, so let's talk about the inverse sine of x. Okay, so the inverse sine of x, well, that's going to equal some y. Okay, and by the way, y is a what in this case? Besides a variable. What does inverse sine
Function.
find?
Derivative. Wait.
What does inverse sine find?
Zero. Inverse derivative.
Has nothing to do with derivatives. You knew this. This is a question you should have answered for me to ask you.
The y. It's the slope.
Oh wait, inverse sine finds an angle. Inverse cosine finds an angle. Inverse tangent finds an angle.
I told you this.
Yes. So, gentlemen,
said that.
would you agree that it finds an angle whose sine value is this x? Correct?
Yes.
Everyone okay with this? So another way to write this is that the sine of that particular angle is going to give you this particular x. Okay? Anyone not? John, inverse sine finds an angle between what and what?
0 and 180. 360.
0.
Let's not just blurt things. If you genuinely have a guess, fine, but not just because you're...
0 and 90.
Inverse sine finds an angle, but only in which quadrants?
Oh, the fourth quadrant.
Oh, first and second.
First
All
and...
snakes teach
third,
Catholics, so
fourth.
it's fourth. Second first.
First
What did
and
you say?
fourth.
No, us smart trick class.
All snakes teach
Catholic
children.
All.
No, it's us
No.
smart trick
All
class.
Calc students take math.
All snakes tease chicken. All students take calculus.
Oh, us smart trick class.
Wait,
Same
what did
thing.
you say though?
All snakes teach Catholics.
What is that?
He's made up his own way of remembering.
Clearly, Chambers do not.
Okay.
Wait, all Calc.
All students
Small
take math.
turkey crows.
Right.
Okay, just to be clear, none of that has to do with what we're talking about. Inverse sine, you may recall, finds an angle in the first and fourth quadrant, and that's from negative pi over 2 to pi over 2. Because otherwise, the inverse sine won't be a function. It turns out that if you take the sine function and you, well, that's not the sine function, it needs to go through it, right? You take the sine function and then you flip it over the line y equals x for an inverse. The inverse is not going to pass the vertical line test, right? Therefore, it's not a function. And so we made it a function by restricting it from negative pi over 2 to pi over 2, and so it turns out that then you just got from here to here. It was a big long thing last year. The point being that inverse sine finds a what? Angle in which quadrants?
First
and fourth, and we're going to call it, and so to make that be connected, we're going to say from negative pi over 4 to pi over 4, as opposed to saying 3 pi over 2 to pi over, because then you go through 2 pi, and then you go jump down to 0 and keep going, right? So we say negative pi over 2 to pi over 2. So gentlemen, y is somewhere less than or equal or greater than or equal to negative pi over 2 and less than or equal to pi over 2. By the way, gentlemen, you do not need to ever prove this again. If you want to write this proof down, be my guest, but I would suggest using the blank page at the back of your packet. Okay? Otherwise, just be along for the ride and just ask questions and make sure that, and my point here, gentlemen, is that I want you to understand that all of this math is within stuff that you have previously studied and is within your understanding. I wouldn't have thought to prove it the way I'm about to. I had to study it for a while before I realized what was going on, but the point is, it's all within your ability. Yes, sir.
So is this finding the slope of the tangent line on a sine function or no?
Inverse sine finds an angle, and all we're trying to do is we're trying to know what is the derivative of that, and so it'd be so the inverse sine function has a particular shape, and we're trying to find what is the slope on that equation. Okay, so inverse sine. So y has to be between here and here because y is the angle. Correct? Everyone okay? So now, if we were to take the derivative of both sides, d dx of sine of y equals d dx of x, what's on the right side? 1. What's the derivative of x? 1. Okay. What's the derivative of this side? Well, gentlemen, this is in terms of y, so and y is a function of x, so we're going to have to use the chain rule. So it's the derivative of sine, which is cosine with g, which is y in this case, left alone, times the derivative of the inside, which is the y, so d dx of y, or just dy dx, or y prime. Is everyone okay with this?
Yes.
So get dy dx by itself, it's equal to 1 over the cosine of y, correct? Now, so here's the derivative. We're done. But wait a second, Mr. Mulheron, that's not what it says. It says it's this whole thing. It's 1 over something, but that whole thing. Okay. Can someone remind me, what is the first basic Pythagorean identity I taught you?
A squared.
Pythagorean identity.
It's
Sine
squared cosine squared equals 1.
Everyone okay with that?
Yes.
T, X, theta, I don't care. How about, could it be Y?
Yes.
Sure. Gentlemen, if I want to get cosine by itself, cosine squared of y is equal to 1 minus sine squared, correct?
Correct.
Y, I guess. And so cosine of y is equal to, you take the square root plus or minus the square root of 1 minus sine squared y. Yes? Don't be the guy who thinks I can take the individual square roots of each individual piece. I can't. Now, wait a second. In the cosine of y, remember, y is an angle in which quadrants? 1 and 4. Is cosine positive or negative in 1? Is cosine positive or negative in 4?
Positive. It's x value.
It's the x value, right? So it's going to be positive. So I can get rid of the negative there. Choose the positive. Hey, so cosine of y equals the square root of 1 minus sine squared. But by the way, John, what is the sine of y? X. So 1 minus x squared.
What? No, I get it. But
Okay. So thus, y prime dy dx of the inverse sine is going to end up being 1 over the square root of 1 minus x squared.
So why did you all of a sudden just go off and do the Pythagorean identity?
Because I wanted to be able to replace this here.
Yeah, but how'd you know how to do that from the 1 over cosine?
Well, like I said, I wouldn't have necessarily known. It wouldn't have occurred to me, and I don't know that it would have occurred to you. I'm just saying that it's all bits and pieces of stuff you do know, right? Now, the thing that I didn't explain as well this time that I did last time is, gentlemen, if I were looking for, if I did ddx of this and ddx of this side, so dy dx is the derivative of inverse sine, correct? So if I find dy dx, that's the derivative of inverse sine. So therefore, this thing must be the derivative of inverse sine. And thus, sure enough, it was. Okay. Again, you are never going to have to prove this on your own. But even if you weren't keeping up super well, I think you've seen that. Hey, I've seen that stuff before. I've seen these other things. It's just all the pieces of stuff that we've been doing, including implicit differentiation, which we learned last time. Nice one.
Where'd you get that X from?
So sine of y is right here. So I just replaced it with x. Yes, sir.
So do all of them use Pythagorean identity?
So all of them, I think they have some form of the Pythagorean identity involved in. Yes.
Your question, I'm looking at like the cosecant and secant ones.
Mhm.
How do you get the absolute value?
So with the absolute value, and without getting too much far afield, because I'm not necessarily interested in getting into them, but there's at some point where we are only allowed to have the positive because of this, that, or the other thing. But x apparently could have been positive or negative in those situations, right? We had where we told us in the last problem we showed you that y had to be between this and this. Well, that has consequences for x, and if x could then possibly be negative, but we need this whole thing to be a positive value based on choices we made. We chose earlier in this problem that, hey, it had to be positive for the square root thing anyways. And so then we'd recognize the fact, the need for that absolute value. If we actually went into the whole proof, we'd see it. I guess I'm not prepared to really explain it well because I'm not doing a good job right now with 2. I think it's further afield than we know. Okay. So at a certain point, so now that we've done this, you can see that we could probably tick these others off pretty easily. This might be a little trickier with the absolute value, but again, I think it's within your wheelhouse if we actually took the time to do it. I don't think it's helpful to. So now that you know that it's at least within the realm of your mathematics already, now we're going to take a step back and say, okay, we're going to take it on faith for all of these others. Good? Okay. So let's do it. Now, here's where I diverge slightly from the way Mr. Westerback was doing. Can you put that with this? Okay, so so if we're trying to find f prime of x equals dy dx of the inverse sine of x squared, okay? So, and again, I'll show you the way Mr. Westerback described this, but I'm going to do it my way first and see if it makes sense. Joan, this is some sort of function, right? And it has an inner function, doesn't it? Mm-hmm. Right? Joan, if this was the inverse sine of a, then what would you say? Well, what's the derivative? The derivative is 1 over square root of 1 minus, you'd say a squared, wouldn't you? Except it's not a. What's in there?
X squared.
So it's x squared squared. Let me pause. Well, there's a little bit going left to go on here, and I'll show you in a second. But so the inverse sine of whatever it is, when it was just plain x, well, then we just had plain x squared there. So if you have something else in there, if it was a, then you have a in there. Or if it has to be x squared, well, then you put x squared in there. Right? Anybody? Yeah?
So, is that a... Actually, no, I think I could... I'm going to
Okay. But, hey, gentlemen, if this isn't just plain x, then we have an inner function g. So this is the chain rule. You take the derivative of this with x squared, g left alone, times dy dx of the inner function.
dy dx or just ddx?
ddx, excuse me, ddx of the inner function. And so now we have 1 over the square root of 1 minus x to the fourth times what?
2x.
2x. We can think of that as over 1. So I have 2x over square root of 1 minus x to the fourth, pardon
Where
me,
do you get the fourth?
x squared squared.
Oh, okay.
Multiply.
Wait, why doesn't the square root cancel with the 2?
You cannot take the square root of each individual pieces. Right? What part is confusing?
No, just the speed, I guess.
Hmm?
I'm having trouble just keeping up with speed.
Yes, sir.
Why do you do a square root?
The square root of 1 plus 3, can we agree is the square root of 4, which is 2? And the square root of 1 plus the square root of 3, that's essentially what you guys are trying to do. You're trying to take the square root of each individual piece. And you cannot do this. This is going to be 1 plus 1.73 or something like that. Is that going to equal 2? No. The point being that the square root of a plus or minus b is not the same as the square root of a plus or minus the square root of b. You cannot take the square root across addition and subtraction of individual pieces. Therefore, you can't say it's the square root of 1 and the square root of x to the fourth separately and say, oh, therefore that's x squared.
No, I'm saying like, why does this one just like spawn? Like it's like. in
It's
second
from
one,
the derivative of the inverse
So
trigonometry.
here's x squared, right? Okay, that is not, so that x squared is this piece, not this one. This comes from the formula that the sign of whatever you've got, that thing gets squared inside the radical here. And it just happens to be that the thing that was, so it's, it's something, whatever, so the sign of whatever, you do 1 minus that whatever squared inside the radical. Well, what is that whatever? That whatever happens to be x squared. Is that helping you out?
Yeah.
Okay, it's our inner function g, if you will. Okay. Now maybe, and I don't know. This is my first. Mr. Westerbeck's got a lot more years on me with teaching calculus. So here's what he's has him do, and so we can do the same. He talks about the derivative ddx of the inverse sine of u. Okay, so he's doing basically the same thing. And so to show the chain rule, here's what he does. He said that is going to be 1 over 1, is the square root of 1 minus u squared, and then ddx of u, which is essentially what we just did. This is just the chain rule, explicitly saying the chain rule, whereas I'm just assuming that we know to use it. And so maybe that is a better way to look at it. Okay? Whichever way makes sense to you, just so you don't forget that the chain rule is going to be necessary. You have an inner function g there, or
So did
u.
you both write-
Does he just want you?
What's that?
Did you both write the same thing? Like, unexplained?
Well, I guess he starts with this and then says, oh, apply it. And I just jumped in it and said, oh, I think they're going to catch the fact that there's an inner function, and so they need to do ddx of that inner function. He calls it u as he goes along, which maybe then makes this less hard to understand. Some of you are really struggling where that x squared come from. That was just the u squared. Okay, so that might be helpful. Okay. Questions? Let's try this next one. So, gentlemen, notice is this a product rule?
Yes.
So inverse tangent is not a number. Inverse tangent is a function, and so this is a function of a function. So we have an inner function.
Good
Right?
product rule on that one, though, right?
So, gentlemen, if you were to use this chain rule, and again, the way Mr. Westerback would write it. So here's this is for this first one. he would write this tangent as that ddx of the tangent, inverse tangent, excuse me, of u is equal to 1 over 1 plus u squared, and then times the derivative of u. Right? That's how he would write it. And so if that helps you as you're writing down the next two things, I wish I had a little more room. I'd like to make a full 3x2 grid like I have over here for the other ones. But I'll go back and deal with that later. But nonetheless, gentlemen, can you use that idea here? I'm gonna write it in again. Check with the neighbor, see if he agrees with you. I think I got mine done in about 3 lines. Just like the last one really was, what, 2 or 3 lines, right?
Yeah, sure.
I'm just going here.
Yes.
Since I totally had a brain fart over the weekend, I do my homework during community time, and I get more than 50%.
Oh, no.
That's every turn.
I give you that.
Yeah.
That olive branch once.
But yeah.
All the branch.
Actually, I was.
I don't even know how I forget that.
You're having a fun time over here. Halloween festivities.
You guys just forgot.
Well, you obviously, like, me and Jeep and Ben were all doing our homework on Saturday.
Word on the street is I saw the Twinkie rolling when he died.
Yeah, it's fine.
Oh, wait, no.
No way, man.
It's not that necessary.
Okay, I'm shutting this recording off. It's not worth it.